Okay, so I think we should start.
Yes. Hi.
Hi. Okay. We'll go ahead and start. So we apologize for the had some trouble with weather here in Beijing, but we're very happy that Professor Jack Xin can be with us today. And so he'll talk to us about some particle and game theoretic methods in numerics. So turn the time over to him.
Okay, thank you. Let me share my screen. Okay, can you see the slides well? Okay, so I'm going to discuss the Lagrangian approach for computing high-dimensional PDE solutions and with multiple scales. So this typically means the solutions will have some singular behavior or small scale and so on. So this is with my team from Singapore, Hong Kong, Quran Institute, and also my colleagues here, especially my colleague Yifeng Yu at UCLI. Okay, so this is an outline of problems. There are three problems in this talk. The two problems came from Kolmogorov in the same year, 1937. So the first one is the so-called Kolmogorov-Petrovsky-Piskunov equation describing flames in fluid flows. And the second problem is the entropy production in time reversal diffusion processes, also by Kolmogorov. It turns out that both problems can be reduced to principal eigenvalue problem and singularly perturbed singular value eigenvalue problem. And both problems have probabilistic interpretation, and not surprisingly, because they all came from Kolmogorov. Okay, so and then the third problem is related to flames in fluid as well, but it's coming from if the first equation is sort of a first principle like PDE coming from physics and chemistry, the third equation, which is called the curvature G equation, is a level set equation that is a simplification of physics and chemistry using geometry. So again, the problem is reduced to a eigenvalue problem in the end. Okay, and in all the equations, the bottom line today is that the Lagrangian point of view is very helpful for computation and also for theoretical analysis. Okay, so let me begin with the first equation studied by Kolmogorov, 1937. So this is the Euro-heat equation, and this is the advection. And then this is the reaction. We choose this quadratic reaction, or sometimes called the logistic reaction, because there is a very special change of variable similar to the Berger's equation. This whole equation, if we use it to describe the spreading of a flame in a particular direction E, we're interested in how fast the flame is moving in certain direction E. For that purpose, we could linearize the equation at the non-equilibrium point, U equal to 0. So therefore, the nonlinearity is actually a linear term. Okay, so if we take this to be U, then the equation is linear. Then we look for a product solution of this form, e to the lambda e dot x. This specifies the direction, and then the speed of propagation is hidden in W. So if we make the change of variable, we derive the equation for W like this, the usual advection, reaction, diffusion equation. And in the equation, of course, there's the lambda, the wave number, as a parameter, and also the direction E. And we look for positive solutions. So you can start with 1 initially, and it evolves in time. So the solution will grow exponentially, and then the growth rate is defined as mu. In general, if the V is a random field with enough mixing, decay of correlation, then one can show that with probability 1, this limit exists. So this is called the principal Lyapunov exponent. And in the simple case, when there's no time dependence, just V of x, and then this mu is simply the principal eigenvalue of the linear elliptic operator on the right-hand side. So mu is the principal eigenvalue, and then the limiting W will be the principal eigenfunction. So that is a much simpler interpretation in the case when V is time independent. Okay. So this is the key quantity. As soon as you find this principal Lyapunov exponent or principal eigenvalue, then the W essentially behaves like e to the mu t. So this behaves like a wave equation, and then a wave solution. And then one can pull out the wave speed, dividing this lambda, you essentially get the formula, which could be rigorously proved. First proved, of course, in the case V equal to 0 by Kolmogorov, but then in 1979, a more general case, spatially periodic or random case could be proved. And after 30 years, my former student Jim Nolan and I proved the general case. Okay, so that's the theoretical development. But today we're more interested in how to compute the mu, in the end, the wave speed. So it turns out that this mu has a probabilistic characterization. So the right-hand side operator is a linear operator. We can decompose it in 2 parts. The second order term and the first order term is a generator of a Markov process. And then the low order term is the potential term. We can write the potential into this form. And then there is a famous Feynman-Kac formula that represents the mu in this form. Okay, so it involves the Markovian part, which is reflected in the sample path of Ito equation. And then on top of that, you have to integrate the Ito solution in terms of this potential in time, and then take the expectation. Okay, so this formula is very beautiful to look at, but not so useful for computation purposes, for scientific computing. How do we make use of this? The main thing is that the key contribution come from a very rare event, and that is when the path happened to visit the maximal point of C, even in the time-independent case. And the rare event is very hard to get numerically. Instead, we are going to look at a normalized version of the Feynman-Kac formula to normalize out the growth. So if we look at the ratio here, you see that this portion is kind of like a measure. So we're integrating this, think of phi as a test function. So this is essentially a moment of the random variable capital X. So therefore, this expression encodes the distribution information of the sample path in time. So we can view this as an evolution operator on the measure. You start with a bunch of points satisfying, let's say, Gaussian distribution. And then as t moves forward in time, this operator would map the distribution into another one. At t go to infinity, it turns out that it'll go converge to, in the weak sense, to the invariant measure, which we call mu c. And if you reach this mu c, you put it into the numerator. In fact, it grows exponentially, exactly at the rate of Lyapunov exponent. Okay, so this is the good property of this normalized Feynman-Kac semigroup, in fact. Okay, so it turns out this is much easier to discretize, and it's much more stable. So we could discretize the Ito equation by the simplest scheme, which is the explicit Euler, and then the integral into sums. So we can formulate certain discrete analog of the Feynman-Kac semigroup, and then we can prove a theorem saying that if the time step is small enough, then you can approximate the original mu pretty well, at least up to some order. Okay, so algorithmically, we can translate this into a genetic algorithm in the following sense. So we have a bunch of particles at the beginning, and they go through mutation, and then evolution of a few generations. Each generation, G, consists of m number of mutations. And what is going on in the mutation to these particles? Each of the particle will go through a advection-diffusion. So that's by Ito equation, just move around a little bit. And then we evaluate its contribution to the potential in the Feynman-Kac. And this biologically, we can think of it as a fitness. So this is the fitness vector. And then we can calculate the mean fitness, take a log and divide by delta t. That gives us the the growth rate of the population in time. And as soon as we have the fitness, which is a vector defined for each particle, we normalize it, define a weight vector p, and we use the p in the multinomial distribution to resample the particles. So these particles will be resampled. So the resampling of the particle it is a selection. So the fitter the particle, the more likely it'll survive to the next round. So so this is the evolution, the genetic evolution. And so after a number of steps of this advection, diffusion, and mutation, we calculate its mean fitness, and then go do this a few generations and calculate the mean fitness. Eventually, over a long time, the asymptotic mean fitness will give us the approximation of the Lyapunov exponent or principal eigenvalue. And then the limiting particle distribution after G generations of mutations will be the invariant, an approximation of the invariant measure. Okay, so this is sort of the algorithmic description of the normalized Feynman-Kac. And the good thing about this approach is that it is mesh-free and it's self-adaptive. The particles will go to where the measure is concentrated. You don't have to do any adaptive grids or anything. And it's not very sensitive to dimension. So go from 2D to 3D, the cost is increased very mildly. Okay, very different from traditional mesh-based methods. However, there is a catch, and that is there is a physical parameter kappa in the problem. So this is the diffusion coefficient kappa. And if kappa is small, then you typically need to put in more particles because the solution gets more concentrated. And also the number of the generation is another factor. You have to evolve long enough to reach the invariant measure. So both quantities add to the computational cost. Okay, so and this brings up naturally the learning problem of the invariant measure, and that is if we do a direct genetic algorithm simulation for a number of physical parameter kappa, can we learn from the solution and then train a mapping that could go from t equal to 0 to t equal to infinity directly without going through all the evolution? So that will be much more effective. So this is what we can do in this framework. So the mapping from t equal to 0 to t equal to infinity is a mapping of the initial Gaussian to the limiting invariant measure, and we don't know what it is, so approximated by a deep neural network. Here we lay out the number of layers, so 12 layers with skip connections, and the network should also be sensitive to the physical parameter kappa. So we also added another auxiliary network here to capture the dependence on the physical parameter. Not as deep, but we put it there just to be sensitive. And then we carry out numerical experiments for 48 number of generations. A time step is here. And then the 50,000 green descent steps. This particle, and take 8 sample values for the physical parameters for training. The training data is produced by the genetic algorithm. And we could do this on not very big neural network with only 5,000 parameters and on a very low-end GPU machine with only 8 GB RAM. Okay, so I need to talk about the flows, the V. So V physically will be 3 dimensions. So here's a standard, a very well-known flow in fluid called ABC flow, which is chaotic. If you take any of these 3 parameters to 0, it becomes a 2-dimensional flow. So it is Hamiltonian. So this is what the projection of the flow to the 2D case. So this is integrable flow and with structures. So for example, closed trajectories and then the connections from saddle to saddle and so on. Okay, and a distinct feature of the 3-dimensional flow is that there's a vortex, a tube-like structure in there. So this tube-like structure is actually helping the particles move. It's like you have freeway. And for both the Kolmogorov flow, when you take only the sine part, the ABC flow will be called Kolmogorov flow. And so this is the Kolmogorov flow. This is the ABC flow with ABC all equal to 1. Okay. All right, and then we did some experiments adding noise to the 111 ABC flow with 100,000 particles and time step kappa equal to 1, and we just want to check if the solutions are meaningful. So if there's no noise, then the growth is linear in terms of the strength of the flow, and this is because of the vortex tube that I mentioned. It helps the flow, the transport, and therefore you get linear growth. So you can see here, the growth rate is nearly 1. But if you add a noise to it, so this is the noise. If you add more and more noise, you destroy the vortex tube, and therefore the motion of the flame will be much lower. Okay, so this is consistent with our intuition. And this is just to show the projections of the invariant measure on 3 planes. So what we really see, this is the cross section. So we see a concentrated area. So this is like a tube. We cut it this way. And if you cut the tube longitudinally, you will see a stretched shape, like something like this. Okay, so the top is when the noise is 0. The bottom, you see, is more blurred, and that's because of the noise effect. And so this is the just to illustration that the solutions get blurred in terms of the invariant measure when you add noise. Okay, so this again is the Kolmogorov flow, and we also add time-dependent term here to make it more strongly mixed. So this way, the number of generations could be a little bit lower in order to converge to the invariant measure. Okay, so so just to show for time-dependent time-periodic Kolmogorov flow, the top is the so this is the neural network generated invariant measure, and this is the training data. And the kappa is smaller on the second column versus the first column. You see that when kappa gets small, the invariant measure is more concentrated from here to here. And also there's resemblance between the generated neural network image and then the ground truth from training data. So that means the network indeed learns the physical solution and then the physical dependence. Okay, So that's for training, and this is for prediction. If you go outside of the training range, when you take kappa even smaller, the left is the prediction, the right is the ground truth. So you see that essentially it does a pretty good job, other than some small errors. Okay, so that's the story of the first Kolmogorov problem. It's a very old problem, but it connects very well with deep learning, and also the particle method turned out to be very successful. And now let me turn to the second Kolmogorov problem. And so Kolmogorov in same year, 1937, considered the following stochastic differential equation with the drift diffusion. And the drift is a sum of the gradient term and then the non-gradient term. So in even dimension, the B would be a Hamiltonian flow. The first term, of course, is a potential flow. Okay, so Kolmogorov asked the question: if you start from t equal to 0, you go forward, and the sample path would be serve as a mapping from the initial measure to samples of the terminal measure at some t equal to, let's say, 100. Okay, so so you have the question: suppose I take the terminal measure and go backward in time, following the same equation. Do I get back the initial measure? And he found out that the answer in general is no, unless this B term is 0, and then that can happen. So so this is the Kolmogorov result. Okay, so this idea was very powerful. It influenced the thinking of statistics, and later on, people thought about, oh, this could be used as a generative model, if that's true. So that means you could, suppose you start the terminal measure as a Gaussian, something you know very well. If you can go backward and then generate something that is non-trivial, that would be wonderful. Of course, you have to make sure that the forward process will go close to the Gaussian in order to be reversible. Okay, so this is essentially the MC sampler is trying to do. And then in recent years, in AI, people propose the so-called diffusion model, which is again very similar to the Kolmogorov idea. So you want to go forward and add noise to your data. Your data distribution is non-trivial, you don't know, but you can add noise to it, go forward in time, and eventually make it approximately a Gaussian. Okay, and then you go backward from the Gaussian. If you're able to extract information of the forward distribution, then you can start with the Gaussian and then regenerate your data. So so this is essentially the idea. But it turns out that going backward in general is going to follow another equation with a correction, and this correction is a score function. So even if you take only the gradient flow going forward, if you you still need the correction in order to generate more accurately the data distribution. So that's a long story by itself. It's a very hot topic in generative AI, and but today, let's go back to the Kolmogorov case when we consider the exact scenario. Suppose you're so lucky you can get started from the terminal distribution exactly, not approximately. Then irreversibility is still a problem. You had to do a lot of work to reverse it simply because there is a Hamiltonian flow, and that is a barrier to reversibility. So to measure the amount of work you have to do, physicists introduced an integral called entropy. So entropy is essentially the Stratonovich product of the Hamiltonian part with the dxt. Okay, so and then the question is to understand the behavior of this random variable, in particular the large deviation of this random variable. Okay, so for large deviation, you can look at the rate function, or another way to approach it is through the moment generating function, which is defined here. Okay, so that's a moment generating function. Turns out that there is an operator form that you could characterize the moment generating function. And this involved a generator. And this generator is advection diffusion operator, very similar to the first Kolmogorov problem. So you have here with a small parameter epsilon in front of the Laplacian, just like the kappa we had before. The epsilon is the magnitude in front of the noise. Okay, so in the weak noise regime, one can do a lot of analysis and then show the following, that the moment generating function is actually growing exponentially with some rate, which we call lambda. And lambda is the principal eigenvalue of that operator I just showed you. And if you're able to get this principal eigenvalue, then just like the first problem, if you take a Legendre transform, that'll give you exactly the growth rate of the entropy or the large division rate function. Okay, so again, we're going to study the computation of this principal eigenvalue. And to make it a little bit simpler, let's make a similarity transform from the operator A into operator B. So operator B has the same principal eigenvalue, only the advection part is a little bit simpler. So again, we have a Markovian part, which is here, and then the potential part, which is here, involving a long expression in V. Okay. And so under the certain assumptions of the growth of the potential, for example, it has to grow at least quadratically and so on, one can show that everything exists well-defined and so on, and then we could play the same game. So we could, again, define the Feynman-Kac semigroup and compute it. And only this time we need a much bigger computer. My co-authors tried it on the cluster machine at Hong Kong University with 96 gigabyte RAM, which is like 10 times more than the first project. So we're going to take 500,000 particles and sample the alpha, the parameter in the moment generating function, essentially from a little bit left of 0 to a little bit right of 1. So on this interval, and then for a few sample value of alpha and so on. Okay. So again, we're going to use some flows because there is Hamiltonian part in this problem. So simplest would be the cellular flow, the Hamiltonian flow I showed you before. So this flow will come up again in the third part. Okay, so and then the potential, we're going to take a double well potential, just like this, with a parameter A in there. Okay, so now you have a well-defined problem. Good news is, how do we know we compute it correctly? In the limit epsilon goes to 0, there is a asymptotic theory. So the formula is known in the limit as epsilon goes to 0. Okay, so this shows you the result. As epsilon decreases, the curves will start from epsilon equal to 0.1, that's the blue, and then gradually go down to the limiting value. So you see it has very good consistency with the exact solution. That's in dimension 2. Okay, so this shows you the 3 epsilon values. As epsilon becomes smaller, the invariant measure become more and more concentrated. So the gradient is very large here. And this actually is cute because it shows 2 isolated supports in the invariant measure. Okay, which is not too common. All right, and so this is for 2 values of alpha, just to make a comparison. All right, so now we could stack up the Hamiltonian flow from dimension 2 to 4, and here it is. And they also do the same with the double well by just adding 2 of them and then go to dimension 4. Again, we could get rather consistent result with the theoretical limit, and this is dimension 8, and then you can go on to 16. The expression gets long, so I just skip the formula. It's just to show that indeed you get consistency. And so this is to show the concentration projected onto the x12, x14 plane on the top and x15 and 16 plane at the bottom. Again, the concentration phenomenon persists as epsilon becomes smaller. All right, and we're curious about the computational time, how it scales with dimension. So we start from 4 to 16, and then it turns out very nicely, the growth of complexity is linear. So that's sort of the holy grail of any methods. If it could grow linearly, that's very nice. as opposed to exponential for classical methods. Okay, so so this is the story with the Kolmogorov, two of the Kolmogorov problems. The first, they're all related to principal eigenvalue, and the first one is related to flame propagation. And now let's go to a sort of another Lagrangian point of view in analyzing the geometric model. So this is called the level-set equation to describe a flame. All the physics and chemistry is involved in this constant, this quantity SL, which is called the laminar speed, and that's the speed from burning by itself. And then there's fluid flow, which in general point in a different direction. So the motion in the normal direction consists of the sum of two parts. One is from chemistry, so that's the SL, what we call the laminar speed. And then the fluid induced speed, which is the projection of fluid velocity onto the normal. So if you translate this motion law into the level set equation, you get this first order Hamilton-Jacobi equation. And it is convex. Think of this as Hamiltonian. It's convex, but it's not coercive. That means the sign is indefinite. So if you had a square here, let's say, then the Hamiltonian will go quadratically at a large gradient, and in that case will be coercive. Okay, so this is the non-coercive but convex problem. What we want to discuss today is the phenomenon due to curvature. So there's, as we often observe, the flame surface is not really straight. In two dimension, we look at a curve. It could be bending. And Markstein in 1951 observed that a point C on the flame surface, flame curve, if it points towards the cold part, so this is the cold, this is the hot. If it points towards the cold, then it moves slower, as opposed to B, which is pointing towards the hot part and moves a little faster. So therefore, curvature introduce a correction, and then this is the correction, 1 minus some constant, and then times the curvature. Okay. And because this term, when curvature is large, it could turn negative, even though it's a correction, we put in a cutoff. And this just to prevent the flame from burning backward, which is non-physical, because when substance is burned, it cannot reburn typically. So therefore, we have a plus. This is very different from melting ice into water, because the water could go back to ice if the temperature is lower. So the process is more reversible, and the flame is non-reversible, and so therefore the plus side here. Okay, so with the curvature correction, the Hamilton-Jacobi equation become more complicated. First of all, the curvature term is a second order term involved here. And it's degenerate. When the magnitude of the gradient is 0, you get some kind of a singular behavior here. Plus, there's a cutoff, introducing another difficulty. Okay, so so the problem becomes non-convex because of curvature, and non-coercive. So there are two nons appearing. Okay, so we're going to study the question whether there is a large-scale velocity. So when t go to infinity, is there a spreading velocity? Just like the first Kolmogorov problem, except the Kolmogorov problem is actually coercive because it could be linearized. So it's like the Burger's equation. And therefore, if you view it Hamiltonian, from the Hamiltonian point of view, it's actually coercive. But this problem is non-coercive. Okay, so if we look at the two-dimensional Hamiltonian flow given by what we call the cellular flow, which is the projection of the ABC flow when A equal to 0, then we prove the first result for this equation this year. So to state it, if you start with the planar data, so you start with a plane like this, the initial flame is just a planar structure, then we show that the solution eventually behaves like a traveling wave. So again, this is P dot X, similar to the first problem, we have E dot X, right? So the P dot X, that's the spatial part, plus some large-scale velocity, which is some unknown quantity that exists, but is highly non-trivial, which we call the effective burning velocity, or in turbulent combustion, they call it the turbulent flame speed. And so this quantity exists times T. So this is the traveling wave. to linear order, and then there's a correction, but it's a low order, so bounded by a constant c. So that's essentially the main result. Okay, so how do you prove such a result? Typically, the strategy is to look at a solution with a correction. So the traveling wave solution is a solution of this form, but it's not an exact solution. In order to make it into an exact solution, you need a correction. So it's often called corrector. So if you plug this into the equation, you end up with the following problem. And the corrector with a v is a solution to this problem with an unknown scalar quantity h bar. And this h bar is the sometimes we call the effective Hamiltonian, or the unknown flame speed. So this is a nonlinear eigenvalue problem. So think of h bar as eigenvalue, the v as eigenfunction. So this is another eigenvalue problem. The only problem is that it is highly nonlinear and non-convex. And we use y here because when you substitute in the time derivative, so this term, the t will be gone when you take one derivative. The x is gone, only this x left, but this x is a periodic variable. So we label it y here just to remind ourselves there's a periodic boundary condition. Okay, so the problem was studied in the 1980s, first by Leon Svardan and Papanikolaou in the coercive case. So, for example, if you have a square here, if you have a square here, then the problem was solved long ago in the 1980s. And the strategy was to introduce this a term called the discount term. So put lambda v here. So lambda v is sort of a regularization term. If you have that term, then there are lots of tricks you can use to show that the solution exists. Question is, if you set lambda to 0, does it converge to a limit? If that converges to a limit and you show that it is y independent, then you essentially recover this h bar, right? So h bar is the limit of lambda v as lambda go to 0. All right. Of course, in their case, they don't have curvature. They didn't have curvature and none of this. And you have a square, so it's very easy to get a gradient bound on the solution and compactness. But in our case, there's no compactness because there's no coercivity. So there's no bound on the derivative, and therefore no compactness. And it's very hard to take a limit by the usual RZ Scully kind of idea. Okay, so here's the strategy. You want to show this has a limit. Nonetheless, how do you do that? So the main analytical contribution in this work is the so-called bounded oscillation inequality. So this shows that the v lambda satisfies this bound. The maximum of v lambda at 2 points, the difference of v lambda at 2 points is bounded by a constant independent of the lambda, without knowing any derivative bound. So if you have a Lipschitz bound, then this is straightforward because you can bound it by a Lipschitz constant times x minus y, absolute value, finish. But we don't know that. Okay, so how do you get this inequality? All right, so so this is where the if you just look at the PDE, it's not going to work. The Lagrangian idea will come in. Okay, so suppose you take the d equal to 0, just go to the convex case, but non-coercive. Even in that case, it's hard to get this inequality from the PDE. So back over 10 years ago, my colleague Yifeng Yu and I studied this problem and realized that the equation is essentially a hyperbolic equation, and therefore there is a generalized characteristics that could describe the solution. And the generalized characteristic is a control family of characteristics. So alpha is the control, and v is the flow. So the trajectory is c. So this is like you row a boat in a lake. So the water is flowing with v, and you have control of the boat. You can move it left and right with certain range of your strength, and you can control the boat to go from point A to point B, right? So that's what you have. So the observation is that if a point, if you the control trajectory can go from x to y, then what happened is that the value of the solution of V lambda at point x, which is the initial point, is bounded by the value of the function at the endpoint through a travel time. Okay, so this inequality is very, it's not too hard to get from integrating this controlled trajectory formula and go back to the equation. So you could derive this inequality. If there's connection from x to y, then you get this inequality. If the trajectory is reversible, you can also come back from y to x. And then, of course, you get a similar inequality with the x, y position switch. If you get both, then, of course, you get the above inequality. And in this work, we managed to show that for incompressible flows, there are indeed connecting control trajectories between any 2 points, and the trajectories are reversible. Okay, so therefore, this inequality is done. Okay, so that's in the curvature-free case. When there's curvature, then the control formulation is no longer good enough. Instead, we need a game characterization. This was due to Kohn-Serfaty back in 2006. They used this to study mean curvature flow to give another interpretation. But we found out this too could be generalized to handle our situation. Just to show the, so it's a discretized formulation. So from time step n to n+1. And the update of the position depends on 2 players. So in addition to in the control problem, there's only 1 player. So that's you sitting in the boat. In this case, there are 2. So the player 1 is the eta, and player 2 is the b. The b only flips signs. It takes -1 to 1. And the eta could be any value under 1 in absolute value. Okay, so this is the, and eta has 2 contributions. One is along the perpendicular direction, because on the plane, you need the 2 directions to sweep out the direction on the plane. So this is the contribution from the 2 players, and this is the flow. Okay, so this is the difference, right? If we have just here 1 term, then we have a control problem. That's a 1-player game, and here we have a 2-player game. Okay, so if the initial data is G, we view this as a payoff function. So the game is to maximize the payoff. In other words, at the last step of the game, we call it X capital N. The value here, we want this, the player 1 want to minimize this value, and the player 2 want to maximize this value. So the 2 are playing the opposite direction, a minimax problem. If they both play optimally, then the final payoff value is very close to the solution of the Hamilton-Jacobi equation. In the limit, as time step goes to 0 and so on, you will converge. So that's essentially the key result of Kohn-Serfaty. And so this is the analytical result. And of course, if both players play optimally, this is called the Nash equilibrium. But the Nash equilibrium is very complicated to reach, very expensive. So in this work, we are just after inequality. So we want a strategy that is easier to carry out. So we want the upper bound on the game value, not the exact game value. So the strategy is for player 1 to control the trajectory from a point P to the point Q. So very similar to the rowing boat scenario, independent of how the player 2 is doing. If this could be carried out, if such a strategy could be found, then we have the following inequality, which is the n value is above the true value of the solution to the Hamilton-Jacobi, and this is the n value Q, and the solution value is P. So we get inequalities. Okay. It turns out that the character problem, even though it's a stationary problem, you can translate into the time-dependent problem through sub-solution technique, and then you could use travel time because if you have a solution of a stationary problem, if you subtract the right-hand side, C, you could create a traveling wave, and that will be a solution to the time-dependent problem, and then you can play this strategy. Okay, so therefore you can develop similar bounds on the stationary solutions as well. So now the key question is, where are the trajectories? It turns out that, remember in the cellular flow, there are these closed trajectories inside the elliptical part. And we found that the game trajectory could go from the inside to the outside. So this always is there. And also the game trajectories could go across the boundary from the edge to the interior. So so this week, even to prove this, you have to use some PDE idea. For example, we found that the game trajectory will go in if the flame is expanding. So so in this case, the normal velocity is going down this direction because the flow is rotating like this. So it's perpendicular to the normal, and therefore v dot n is 0. And then the curvature term, because the surface here is flat, is nearly 0. So therefore, the normal velocity is essentially 1. So the flame will be expanding, and therefore the game trajectory will go in, and so on. Okay, so by using this idea, we could prove the following inequality, that if you start with the planar data, the true solution minus the initial data, the growth part, is bounded from above by minus a constant times t plus c. Okay. And so these could be established, and there's a similar reversion for the stationary solution. If we divide this by t, 1 over t is essentially the lambda, the discount parameter, and you prove something similar. Okay, so all of these, so what are we doing is to go from the Lagrangian, the trajectory kind of information, to the solution of the PDEs now. Okay. As soon as you have that, if lambda is small enough, you can get a lower bound on the discount term and get the differential inequality on the PDE. And this differential inequality immediately shows that the P plus dv lambda can only reach a minimum on the domain at the boundary. So this is what we call the minimum principle, because if it reaches in the interior, the first derivative will be 0. It cannot be greater than a positive number. Okay, so the minimum principle is what we extract eventually from the Lagrangian, the game information. And in the meantime, we still have the game interpretation solution. So, okay, just to show you how this works, to give you the bounded oscillation inequality. So when we go look at the interior first. So suppose we have a point y inside a domain like this. And we know that there is a game trajectory that could go from inside out to a point x on the boundary of this domain. All right, so by the game interpretation of the solution, the stationary problem, we have this game inequality. And that is the value of the solution at the endpoint, the x, bound the value at the initial point up to a constant. So this is the first inequality from the Lagrangian side. As soon as we have this, if this is true for any x and y, we take the mean over here on the boundary and take the max over y in the interior, then we get the following. The minimum value of the u lambda, the solution, on the boundary is bounded from below, but the maximum of the value function in the domain up to a constant c. Okay, but the problem with this is that it's not the oscillation inequality here yet, because the left-hand side is on the boundary. The right-hand side is the whole domain. However, the minimum principle says that the minimum is actually on the boundary. So the minimum on the boundary is the minimum on the whole domain. So therefore, we have the minimum and the maximum being compared directly. So if you move this to the right-hand side and the c to the left-hand side, then you essentially get the max minus mean on the entire domain is bounded by a constant c. So this finished the inequality in the interior case. And you can see here the coordination of the Lagrangian information with the PDE information, or the Eulerian thinking. So the Lagrangian and the Eulerian thinking go together, and then you get the bounded oscillation inequality. So this is for the interior. similar arguments, more elaborate, have to be done near the boundary, and altogether you get the result. Okay, so it's time to conclude. We have introduced a interacting particle framework to compute principal eigenvalue and eigenfunctions in high dimensions. Physical dimension is 3 in the first problem, but in the second Kolmogorov problem dimension, it could be as high as you like. And the methods scale linearly. And deep learning framework could be naturally introduced to speed up the calculation with physical parameter dependence, even though the neural network doesn't have to be very big. But of course, we could do more if we generate more data. And also we show in a theoretical work that the Lagrangian thinking is very helpful, and this is reflected in the game interpretation of PDEs. And we're currently trying to carry out this particle and deep particle framework for a cancer cell spreading problem. So it's similar to flame spreading, but you have cancer cell spreading, and turns out that could be studied in this framework as well. And also the three-dimensional problem of the curvature G equation is much more challenging. That will involve a three-player game. And so far it's widely open. And we hope to make progress maybe in the next 10 years. We already found a counterexample in 3 dimensions that for simple shear flows, the answer is no. So therefore, it's more delicate than 2 dimension. In 2 dimension, we could more or less show for all the flows, this framework will construct a solution. But in 3D, it's not known yet what's going to happen. Okay, thank you very much for your attention.
Okay, thank you very much. Any questions? So I had a question you sort of mentioned in your last slide here. You mentioned these other potential applications. I'm curious if you have any feeling as to whether these kinds of methods could be applied to other types of equations.
That'll be very nice. So so far, the equations should have certain probabilistic interpretation. If it's independent probability is difficult. So either it has some resemblance to the Fokker-Planck equation, like in the cancer spreading problem, the equations are kind of like Fokker-Planck in some sense. So therefore, there is a probabilistic interpretation. Therefore, all the stuff will come in. Another class of problem where we could identify a similar structure is the chemotaxis system, the Keller-Ziegel chemotaxis system. There is interacting particle description of the solution. So the PDE essentially is the Makin-Vlasov macroscopic limit. So in that setting, we could play the same game. Yeah. So so that's another talk, of course. But we are exploring the Keller-Ziegel systems. Also in kinetic theory, one has the the PDE, the Boltzmann equation. But of course, physically speaking, the Boltzmann equation is a reflection of a microscopic evolution of particles. So some physicists actually studied certain aspects of the Boltzmann equation through interacting particles. So that area I haven't gone into yet, but I would imagine something similar could be done.
Cool. I see. Thank you very much.
Thank you.
Okay. Well, we're very happy to have you here and hope to see you in person sometime.
Sure, sure. Enjoy your time in Beijing and stay dry.
Yeah, thank you. We'll do our best.
Thank you. Sure. Thank you.
Okay.
Bye-bye.
Bye now.
Bye.